Mechanics refers to study of interactions of material bodies, and under mechanics, largely we can think about two different types of mechanics, and statics and dynamics. Motion is what make everything happen. Right now on the right side, you see very simple three images: the two square and cow and ball with the shade and so on. But it's very interesting. If you show this image, a newly sighted people, which means for their life, for the entire their life, they have been blind, and they regain their sight. The first time they see these kind of images, okay, they are unable to organize many regions or different colors and brightness into large assemblies. That means if you look at these two square, you know that the two square is overlapped, but to them, this one just perceived as a separate object. Like this one, they just perceive this is a black regions and white regions and black, and this is red and shaded area. They cannot perceive this as a large one meaningful entity. So why is this so? Because in a healthy subject, or if you have normal sight, then since our brain is kind of trained as you see some moving object. So these confusing regions gelled into the meaningful structure with the introduction of one particular visual cue, which is a motion. Let me show you this one. What do you see? So you see very different kind of dot area. But if I make a motion, as soon as you see the object is moving, you see clearly this is one kind of entity with the edge. You see the very clearly see the edge. Likewise, our brain has been trained in such a way when some object has emotions that can be perceived as one meaningful entity. And then under dynamics, we talked about two different types of dynamics, kinematics and kinetics. And kinematics, we don't consider the cause of the motions. We don't consider the force and torque applying on the body. We just only consider how we analyze the motions using velocity and accelerations, whereas the kinetics, we include the force and torque and relate those kind of force and torque to the motion. And then we talked about different types of motions in the rigid body, and firstly, translational motions. So translational motions, we have two different types of translational motions, rectilinear and then curvilinears. So those translation refers to not rotations. Okay. So the rectilinear is just the straight motions. Curvilinear is curved motions. However, there's no rotations. So if you look at these two arbitrary point is connected by one line, and then after this body undergo the motions, these two line is still parallel, which means this rigid body does not undergo any rotational motion. And then this is rotational motion. So right now two gears are rotating about the axis here. And then the first example is centroidal rotations. The centroidal means the rotating axis here, okay, this rotating axis is aligned with the center of mass of this object. So this is a circle, that's why the center of mass should be on the center, but rotating axis is aligned with that, and this one too. So rotating axis is aligned. And non-centroidal rotation is that, let's say your pivot point, rotating point is A, but the center of mass should be around here, for example. Let's say this is center of mass. then center of mass is not aligned with the axis of rotations. So we call this non-centroidal rotation. And then I just want you to clearly understand what rigid body as opposed to the particle. The rigid body means our bodies are rigid. So if you apply the force on this kind of body, okay, then this one is kind of moving. A certain point later, it just moved. This is position 1, position 2. So your force are involved in change of the motions. However, the force does not involve in the deformation of the object. So we assume there's no deformations. So that's the rigid body. And particle is a point of mass. So the point of mass doesn't have any shape. Okay. So because this one doesn't have any shape, rotating of this particle can be a mute point. So how can we rotate this particle? So we cannot, right? It has only the mass. So this is particle. Okay. And in dynamics, these are general kind of steps to analyze analyze the object in dynamics. We describe the motion and equations, the motion. We come up with equations of motions and then apply the math. Dynamics is a branch of physics, and then physics is a model. So what does they mean by the model? That means you can change your model. So dynamics is help us to understand and interpret a lot of natures, but we have many different models to understand exactly same nature. So in the dynamics, we talked about, for example, second Newton law. So Newton contributed a lot in the dynamics, but we can take another model to understand or analyze the object in motion. So first, let me think about a simple object. So right now, the mass is hung by the ceiling through the spring. Okay, the spring constant is K. And then I want to set my reference point. So this is my reference, and this is at rest. So if you stretch it to the x coordinate here, then this body will kind of move, okay? And then the spring is stretched. And then if you let it go, this one is going, just moving up and down, okay? Let's say, and then let's say this is a ground, okay? Then for our convenience, going down is the positives. Then how we write equations of motion. So I want to describe these motions, okay? Then I want to write the equations of motions. So if you look at the mass, okay, what's the force acting on this body? So we have a spring force, okay? Then spring force is equal to spring constant and stretched length. And what else? We have the mass gravitational force, which is mg. So these are all the external force acting on this body. And according to the second Newton law, all the external force acting on the body is equal to ma, acceleration, right? And then what is acceleration? Acceleration is the derivatives of the velocity, right? Derivative of the velocity is accelerations. And what is the velocity? the velocity is the derivative of the position. So that's why this one becomes second derivatives of the position, or simply we can say x2 dot. Okay, the x2 dot represent second derivatives of the position. So if you just write the equations, then this is minus kx plus mg is equal to mx2 dot. So this is the equations of motion. Okay. So from here, if you want to calculate the accelerations given your position, or then you can easily calculate that and so on. But I told you that we can take another approach, which is energy method. So there's a physicist whose name is Lagrange. He was born in 1788, and he looked at this problem with a new, different way. So you know that the energy consists of kinetic energy and potential energy. So if you look at all the energy term involved in these motions, what kinetic energy we have? We have a kinetic energy is mass times the velocity squared. That's kinetic energy of that object. And how about the potential energy? So when this one is stretched, the spring force, because the spring is stretched, the potential energy of the spring is increasing, right? So that is 1 over 2k stretched length square. But this one is going down because this is more close to the ground. The potential energy is decreasing, so mg, and then let's say, because this is our reference, that's why you can just put the x. So these are all the energy term. Then the external force acting on this body are only spring force and gravitational force. These two forces are conservative forces. That means your energy term will be conserved as long as conservative forces are involved. Because there's no any frictional force, we ignore the resistance of the air. That means your energy is conserved. Means the time rate of change of your energy should be 0. Okay. So let's take first derivatives of this term. So what is the v? So I told you that the v is x1 dot, because the velocity is first derivative of your coordinate x. So if you just replace this term with this one, then let's take dt over dt, dE over dt. Then I want to because this square is going coming front, and then if you use the chain rule, you have to take another derivatives. So this is chain rule. I'm going to talk about that and then if you take another derivatives, this is k and x dot, this is under chain rule, and mg x dot, and this one should be 0. Surprisingly, this term is the exactly same as this one. So let's say this is 1 and this is 2. So now 1 is equal exactly same as 2. So I told you that when you take Lagrangian approach, which is energy, and this is classic Newtonian approach. and we can't reach, we just have exactly same equations, okay? Then you apply the math. And then surprisingly, we have another approach. Another approach is that momentum. Okay? We use the momentum. So what is the momentum? Momentum is mass times velocity. Okay. So in the momentum, let's say you have a mass, and then you apply a force. Then this is first positions, and then let's say this one has a certain velocity. Then the second position, because we apply the force, it changed the velocity. Okay. So according to the principle of momentum, the momentum change between the first and second position is equal to the time integrations of the force, which means your momentum change P2 minus P1 is equal to time integration of your force acting on the body. So which means mv2 minus mv1 is the force, whatever the dt. So dt is from, let's say time is 0 here, so this is certain time t, so from 0 to t1. So if you apply this one to the pendulum problem that we have, so initially our x is 0, and then this is let's say x dot, right? And is equal to what is our force? Your force was that was our force, right? From tt. Then this is a principle of momentum. So let's take time derivatives on both sides. Then which means on the left side it becomes 2x dot. And then if you take a time derivatives on the right term, this will just dt will just gone. So this one just become simply like that. So you see that this is exactly the same as our previous equations of motion. So either we take Newtonian class Newtonian approach and energy approach or momentum approach, we end up having exactly the same equations of motion. So in here, in the dynamics, we first learned motion of particle. Okay, so that means it's very simpler than the motion of rigid body, because in the particle we don't need to think about the rotation. And then I told you that in the dynamics there is a kinematics and kinetics. So we first learn about kinematics for motion of particle, then move on to the kinetics. Then on the kinetics, when you come up with or write equations of motions, you can take a different approach. The Newtonian approach, classical Newtonian approach, or Lagrange approach, which is involved, energy method is involved, and the momentum method. So we lay out our textbook. Chapter 12 is about kinematics of motion of particle. Chapter 16 is kinematics of rigid body, so we add the rotation here. So I'm going to cover kinematics first and then moving on to the kinetics.